Somewhere in the constellation Hercules, roughly 1,200 light-years from Earth, there exists a planet more than twice as wide as Jupiter. At that scale, you might expect a crushing giant. A world defined by overwhelming gravity and raw force. But that expectation doesn't hold. HATP 67b has less than half the mass of Jupiter. Its density is even lower than a marshmallow. Observations in recent years show that its atmosphere is actively escaping into space at a rate of about 10 million tons every second, forming a faint, ghost-like stream of helium that stretches more than 130 times the planet's own radius. Over the course of a few 100 million years, it is expected to be consumed by its aging star. This is not the largest planet in the way we tend to imagine. It is something far more unusual. A world so inflated that the term planet begins to feel uncertain. So, take a moment to settle in. Get comfortable, and let's begin. Close your eyes for a moment and picture the largest planet in the universe. Whatever your mind creates, it isn't quite right. And that small mistake reveals something deeper about how we think about size, about power, and about what a planet is meant to be. So let's begin with what you likely imagined. Something enormous. Something incredibly heavy. A world with gravity so intense it could crush spacecraft and pull in entire moons. In your mind, it was probably just a scaled-up version of the largest planet you already know. A bigger Jupiter. That instinct is completely natural. Jupiter is the ruler of our solar system, and everything about it suggests dominance. It is 11 times wider than Earth. You could fit more than 1,300 Earths inside its volume and still have space left over. Its mass is 318 times that of our planet. In fact, it outweighs every other planet, moon, asteroid, and comet in the solar system combined, and then effectively doubles that total. Jupiter is not just the largest object orbiting the Sun. It acts as the gravitational anchor that helped shape the structure of the entire solar system. If you could somehow stand on its cloud tops and survive, you would weigh about 2.5 times more than you do on Earth. The pressure beneath those clouds rises to extremes that could crush a nuclear submarine in seconds. Winds tear through the atmosphere at around 350 miles per hour. And the Great Red Spot, a storm that has persisted for centuries, is so vast that Earth could fit inside it with room to spare. Lightning within Jupiter's atmosphere releases energy thousands of times more powerful than lightning on Earth. The radiation belts surrounding the planet are so intense that an unprotected human would receive a fatal dose in just minutes. This is a world defined by overwhelming force. Jupiter's gravitational influence stretches far into space, allowing it to capture 95 known moons, some large enough to be considered worlds of their own. Ganymede, the largest of these, is even bigger than the planet Mercury. Europa, hidden beneath a thick shell of ice, contains a global ocean that may hold more liquid water than all of Earth's oceans combined. Io, constantly pulled and compressed by tidal forces, erupts with volcanic activity unlike anything else in the solar system. In this way, Jupiter is not only powerful, it is also a kind of cosmic guardian. Its immense gravity deflects comets and asteroids that might otherwise strike the inner solar system. Without Jupiter, Earth would likely experience far more frequent impacts from large objects. Some scientists suggest that the presence of a gas giant like Jupiter may have helped create the stable conditions necessary for complex life to emerge here. So Jupiter does not simply dominate the solar system, it may have quietly made life possible, and this is where our intuition begins to form a very specific expectation. If Jupiter is already this powerful at 11 times the width of Earth and 318 times its mass, then the largest planet in the universe should be all of this multiplied. It should be larger, heavier, denser, more extreme, a more intense version of Jupiter, stronger storms, more crushing gravity, harsher radiation, and even more moons. Everything about it should represent the absolute limit of what planetary physics can create. And this expectation is not accidental. It follows a pattern we see throughout nature. Larger elephants are heavier than smaller ones. Taller skyscrapers require more material than shorter ones. The biggest stars contain more mass than average stars. As things grow in size, they tend to grow in strength as well. Mass increases with volume. Strength tends to scale with mass. This pattern appears almost everywhere in human experience. And for a long time, it seemed to apply cleanly to planetary science as well. For centuries, astronomers recognized 9 planets, and later 8 after Pluto was reclassified. The pattern felt simple and reliable. The rocky planets closer to the Sun were small, but denser. Earth, the largest among them, spans roughly 8,000 miles in diameter and has a density of about 5.5 grams per cubic centimeter. Farther out, the gas and ice giants were much larger and less dense by comparison, yet still incredibly massive. At the top of this structure sat Jupiter, the biggest, the heaviest, and the most gravitationally dominant. The link between size and mass seemed consistent, almost like a natural law. But as astronomers began discovering planets around other stars, that assumption started to break down. The first confirmed exoplanet orbiting a Sun-like star was found in 1995-51 Pegasi b, detected by Michel Mayor and Didier Queloz using radial velocity measurements at the Observatoire de Haute-Provence. At the time, the discovery was deeply surprising, though today it may seem almost familiar. 51 Pegasi b was a gas giant with about half the mass of Jupiter. Yet it completed an orbit around its star in just over 4 days. That placed it far closer to its star than Mercury is to our Sun. No one expected to find a Jupiter-like world in such an intensely hot environment. According to prevailing models of planet formation, gas giants were thought to form far from their stars, in the cold outer regions where ices could gather and build large planetary cores. Finding one so close to its star was like discovering a snowman standing inside a furnace. And that discovery changed everything. In the years that followed, astronomers began finding many more of these worlds. Massive planets orbiting extremely close to their stars. Exposed to intense heat, they became known as hot Jupiters. These planets quickly revealed something unexpected. The relationship between size and mass was not as straightforward as once believed. Some hot Jupiters were heavier than Jupiter, yet similar in size. Others were lighter, but noticeably larger, and a few were far wider than Jupiter while containing only a fraction of its mass. The clean pattern observed in our own solar system turned out not to be universal at all, but rather a local coincidence. As detection methods improved, the catalogue of known exoplanets began to grow rapidly. Transit photometry, where astronomers observe the slight dimming of a star as a planet passes in front of it, made it possible to measure planetary size with high precision. At the same time, radial velocity measurements, which track the subtle wobble a planet causes in its host star, allowed scientists to estimate planetary mass. When these two methods were combined, they offered something entirely new: the ability to determine the density of distant worlds. And what those densities revealed was unexpected. Some gas giants showed values similar to Jupiter, around 1.3 grams per cubic centimeter. Others were far less dense, dropping below 1 gram per cubic centimeter, even lower than the density of water. And a few were so diffuse that their existence seemed almost physically implausible. There were planets with the volume of Jupiter but less mass than Saturn, worlds as wide as giant planets, yet with a structure closer to something like heated mist. These became known as inflated hot Jupiters. Planets expanded far beyond what their mass alone should allow. According to standard models, a gas giant of a given mass and age should gradually cool and contract to a predictable radius over time. Those models work well for cold gas giants orbiting far from their stars. But for planets in tight orbits, exposed to intense stellar radiation, the predictions consistently fall short. The observed planets are simply too large, not by a small margin, but by 20, 30, sometimes even 50% or more. This mismatch became one of the central problems in exoplanet science. So what is causing these worlds to expand beyond expectation? Where does the additional energy come from, and why do some hot Jupiters become dramatically inflated, while others in similar environments remain relatively compact? The questions began to grow faster than the answers. Several possible mechanisms have been proposed. One is ohmic dissipation, where electrical currents generated by atmospheric winds moving through a planet's magnetic field deposit heat into its interior. Another is tidal heating, where gravitational interactions between the planet and its star flex the planet's interior, producing friction and heat. And a third involves atmospheric circulation, where powerful winds transport heat from the intensely irradiated dayside deep into the planet, preventing it from cooling efficiently. Another proposed factor is enhanced atmospheric opacity, where certain chemical compositions trap heat more efficiently than standard models would predict. Each of these mechanisms can explain part of the observations, but none of them fully account for the entire range of inflated planet sizes that astronomers have measured. What gradually became clear, even as the details remained uncertain, is that proximity to a star fundamentally reshapes what a gas giant can become. A gas giant far out in the cold regions of a planetary system behaves much as textbooks describe. It forms, it slowly cools, and over time it contracts to a stable size determined by its mass and composition. In that distant environment, it can remain largely unchanged for billions of years. But move that same planet inward to within just a few stellar radii, and the situation changes completely. Intense radiation from the star continuously injects energy into the atmosphere. Somehow, that energy finds its way deeper inside. Through processes that are still not fully understood, the planet begins to expand. Its density decreases. Its internal structure shifts into something that Jupiter itself would not resemble. And this is the key idea that often goes unnoticed when we hear the phrase largest planet. The word largest carries an assumption. We tend to think it means the most massive, the most powerful, the most extreme in every physical sense. We imagine that the largest planet must also be the heaviest, a kind of super Jupiter that makes our own gas giant seem small by comparison. But mass and radius are not the same thing. They describe different aspects of a planet. A world can have an enormous size while containing far less material than expected. This happens when something prevents it from contracting. If energy is added to the interior faster than it can escape, the planet expands, becoming vast in volume, yet surprisingly light in substance, more like a cosmic balloon than a dense, compact sphere. Because of this, the search for the largest exoplanet becomes more subtle than it first appears. Are we looking for the most massive world? the one that contains the greatest amount of matter. That path leads toward planets many times heavier than Jupiter, dense, powerful, and gravitationally intense. Or are we searching for the widest planet, the one with the greatest radius? That path leads somewhere very different, toward inflated worlds, where size and substance no longer scale together in familiar ways. And that distinction matters. The most massive planets are certainly impressive, but they are not especially surprising. They are simply an extension of known physics: more mass, more gravity, more pressure. But the widest planets, the most inflated ones, are something else entirely. Their size does not come from accumulating more material. Instead, it comes from that material being stretched, heated, and expanded into forms that no cold planet could ever sustain. They are shaped by extreme environments, by proximity to their stars, by conditions that transform what should be a simple sphere of hydrogen and helium into something far more unusual, something almost alien. As of today, astronomers have confirmed more than 5,700 exoplanets. The catalogue reveals an astonishing diversity: rocky worlds smaller than Earth, super-Earths with no equivalent in our solar system, Neptune-like planets wrapped in thick atmospheres, ice giant, gas giant, worlds orbiting two stars at once, and planets so close to their stars that their surfaces may be covered in molten iron rain. There are also planets that exist at the opposite extreme, worlds so distant from any star that they drift through interstellar space in permanent darkness. The range of possibilities is remarkable, and within this vast catalogue, astronomers have identified a small group of planets that sit at the very edge of size. Not the heaviest worlds, but the widest. These planets tend to fall into a very specific category. They are almost always hot, highly irradiated gas giants in tight orbits. They are almost always inflated far beyond what their mass alone would suggest. And perhaps most surprising of all, some of them are not even as massive as Jupiter. That point is worth pausing on. Several of the largest planets ever measured by radius are actually lighter than Jupiter, in some cases. Significantly so. Their enormous size does not come from containing more material, but from that material being stretched across a volume far greater than physics would normally allow. They are, in a sense, like cosmic cotton candy, vast, diffuse, and inherently fragile. And among this unusual group, one planet stands out above all the others, a world that sits at the very top of the radius scale in the NASA Exoplanet Archive, occupying a region of the mass-radius diagram where almost nothing else can persist for long. It is not the heaviest planet, nor the densest, nor the most gravitationally intense, but it is one of the most swollen, most oversized, and most structurally delicate objects ever classified as a planet. Its name is HAT P67b. It orbits a dying star in the constellation Hercules, about 1,200 light-years from Earth. This planet was discovered by the Hungarian Automated Telescope Network, using small wide-field telescopes at two observatories, the Fred Lawrence Whipple Observatory in Arizona and the Mauna Kea Observatory in Hawaii. Initial observations were made in 2005 and 2008, with follow-up transit measurements recorded between 2011 and 2013. Its confirmation and full characterization were published in 2017. And when astronomers examined the data, something did not seem to fit. HAT-P67b has a radius of approximately 2.14 times that of Jupiter. Just pause on that for a moment. This planet is more than twice as wide as Jupiter. If placed side by side, it would dwarf the largest planet in our solar system, in much the same way Jupiter dwarfs Earth. Its volume is roughly 10 times that of Jupiter. If the largest planet in our solar system were the size of a basketball, then HAT P67b would be more like a beach ball placed beside it. By any measure of size, this is one of the largest planets ever confirmed. The NASA Exoplanet Archive places it among the widest planets known. In terms of sheer physical scale, it is a world that makes Jupiter seem almost ordinary. But this is where the story begins to shift, where our expectations about what the largest planet should be start to fall apart. HAT P67b is more than twice the width of Jupiter. Yet, it does not come close to matching its mass. In fact, it is not even comparable. The most recent measurements, published in 2025 using the NEED spectrograph on the WIN 3.5-meter telescope, estimate its mass at around 0.4, 5 times that of Jupiter. Less than half Jupiter's mass, roughly 1.5 times the mass of Saturn, yet more than twice Saturn's width. Take a moment to hold those numbers together. A planet more than twice as wide as Jupiter, but weighing less than half as much. The result is a density so low it almost seems like an error, about 0.061 grams per cubic centimeter. To understand how extreme that is, consider the comparison. Water has a density of 1 gram per cubic centimeter. Jupiter is about 1.33. Saturn, the least dense planet in our solar system, is still around 0.69. A marshmallow, depending on its composition, typically falls between 0.1 and 0.15 grams per cubic centimeter, and HAT P67b is even less dense than that. This is not what we expect when we imagine the largest planet. It is not a crushing giant or a gravitational powerhouse. It is something very different. This is a world so inflated, so stretched beyond its natural state, that it is barely held together. A planet made more of emptiness than substance. A gas giant where the word giant refers only to its size, not its weight. And it becomes even more extreme when you consider where it exists. HAT P67b is not quietly orbiting in the cold outskirts of a distant system. It resides in one of the most hostile environments a planet can endure. It orbits its star at a distance of just 0.065 astronomical units, roughly 10 million kilometers. For comparison, Mercury orbits the Sun at about 58 million kilometers. This means HAT P67b is nearly 6 times closer to its star than Mercury is to ours. Its orbital period is just 4 days and 19 hours. While Earth takes an entire year to complete one orbit around the Sun, this planet circles its star 76 times in that same span. And the star it orbits is far from calm or stable. HAT P67 is an F-type subgiant, with about 1.73 times the mass of our Sun and roughly 2.65 times its radius. It is a star that has already begun to evolve beyond the main sequence, expanding as it gradually exhausts the hydrogen fuel in its core. It rotates rapidly, with a projected velocity of nearly 36 kilometers per second. Its luminosity is about 12 times greater than that of our Sun, and it continues to grow brighter over time. All of this means the planet is being intensely heated. Its equilibrium temperature is close to 1,900 Kelvin, placing it right at the boundary between what astronomers classify as hot and ultra-hot gas giants. At such temperatures, molecules in the atmosphere begin to break apart. Chemistry shifts away from familiar molecular compounds and becomes dominated instead by individual atoms and ions. The day side of the planet glows under this extreme heat, and in response, the planet itself is changing in a dramatic way. It is beginning to come apart. But that part of the story, a world slowly losing its atmosphere into space, forming a faint stream of helium stretching across millions of kilometers. is something we will return to shortly. For now, just sit with the paradox. The largest planet known by radius is not a larger version of Jupiter. It is not heavier, not denser, and not more powerful in terms of gravity. In many ways, it is the opposite of what we expect. A world of immense size built from surprisingly little mass. It is enormous not because it has gathered more material, but because it has been inflated, expanded, stretched beyond what seems reasonable, shaped by forces that have less to do with accumulation and more to do with circumstance. In a sense, it is a planet made large simply because it exists in the wrong place at the wrong time. So the largest planet is not the strongest one. And that reversal, simple as it sounds, is where the deeper mystery begins. What follows is the story of how this unusual world was discovered, why its measurements puzzled the scientists who studied it, and why a follow-up study in 2025 suggests that it is now moving toward an irreversible end. And its discovery was not a sudden breakthrough or a dramatic moment. It was something much quieter, a gradual collection of data gathered over many years. Using small telescopes that most people might pass by without ever noticing, the instruments responsible for discovering one of the most extreme planets in the known universe were not massive, billion-dollar space telescopes. Instead, they were modest ground-based cameras with apertures of just 11 centimeters, about the size of a large coffee can lid. But they had one crucial advantage: patience. And in exoplanet science, patience is everything. The Hungarian Automated Telescope Network, known as HATNET, operates a set of these small, wide-field instruments across 2 locations. One group is based at the Fred Lawrence Whipple Observatory on Mount Hopkins in southern Arizona. The other observes from the summit of Mauna Kea in Hawaii. Together, these telescopes monitor hundreds of thousands of stars at the same time, searching for the subtle dimming that occurs when a planet passes in front of its host star. From our perspective on Earth, this method, known as transit photometry, is conceptually simple. When a planet crosses the line of sight between its star and the observer, it blocks a small fraction of the starlight. The depth of that dimming reveals the planet's size relative to the star, and the timing between repeated events reveals its orbital period. HATNET began observing the star, now known as HAT P67, in 2005. With additional data collected in 2008, the measurements showed regular dips in brightness, consistent with a large object transiting the star every 4.81 days. The depth of these transits suggested that something unusually large was passing across the stellar surface. Follow-up observations, using a larger 1.2-meter telescope at the Fred Lawrence Whipple Observatory, captured a full transit on May 28, 2012, along with 5 partial transits recorded between 2011 and 2013. The signal was clear, repeatable, and significant. But detecting a transit alone is not enough to confirm a planet. In exoplanet research, transits by themselves are not definitive proof. There are several astrophysical scenarios that can produce similar signals and mimic the presence of a planet, a faint eclipsing binary star in the background, blending with the light of the target star, can create periodic dimming signals that look almost identical to a planetary transit. A brown dwarf, an object too massive to be considered a planet, yet not massive enough to sustain hydrogen fusion like a true star, can also pass in front of a star and produce a similar pattern. To rule out these false positives, astronomers need to measure the mass of the transiting object, and this is where HAT P67b became particularly challenging. The standard method for determining an exoplanet's mass is the radial velocity technique. As a planet orbits its star, its gravity causes the star to wobble slightly. This motion shifts the starlight towards shorter, bluer wavelengths as the star moves toward Earth, and toward longer, redder wavelengths as it moves away. By tracking these subtle shifts in the star's spectrum over time, astronomers can estimate the mass of the orbiting companion. The method is remarkably precise. Modern instruments can detect stellar motions as small as less than 1 meter per second, slow enough that a person walking at a relaxed pace would move faster. But this technique comes with a limitation. It relies on clean, stable spectral lines. If the star itself distorts or blurs those lines, the planetary signal becomes difficult to isolate, and HAT-P67 is exactly that kind of star. It is an F-type subgiant rotating at a projected speed of nearly 36 kilometers per second. For comparison, our Sun rotates at about 2 kilometers per second. That means HAT-P67 spins roughly 18 times faster. This rapid rotation spreads out its spectral lines, turning them into broad, shallow features that make precise measurements far more difficult. As a result, the tiny wobble caused by a planet with less than 1 Jupiter mass becomes buried within the noise created by the star's own rotation. Early radial velocity measurements, collected at the KK Observatory between 2009 and 2012, were unable to determine an exact mass. They could only place an upper limit on how massive the object might be. The transiting object was estimated to have a mass of less than 0.59 times that of Jupiter. This was enough to rule out a stellar companion or a large brown dwarf, both of which would have produced a much stronger wobble in the star. But it still left the true mass uncertain. The object could have been anything from a small fraction of Jupiter's mass up to that upper limit, and that difference matters, because depending on where within that range it fell, the nature of the object would change significantly. The confirmation ultimately came through a different method, one known as Doppler tomography. Rather than measuring the overall wobble of the star, this technique tracks how the planet's shadow moves across the rotating surface of the star during a transit. As the planet passes in front of the star, it blocks light from a specific region of the stellar surface. Since different parts of the star are moving either toward or away from us due to rotation, the light from each region carries a slightly different velocity signature. By observing how this blocked signature shifts over time, astronomers can map the motion of the planet's shadow across the star. This allows them to confirm that the dimming is caused by a compact object crossing the stellar disk, rather than by a background binary system or an observational artifact. Two independent Doppler tomography detections confirmed the signal. The object was indeed a planet. These observations also revealed something about the planet's orbit. It is closely aligned with the rotation of its host star, within roughly 12 degrees in projection. That alignment offers an important clue about its history. It suggests that HAT-P67b likely migrated inward through interactions with the protoplanetary disk early in the system's formation, rather than being scattered inward through violent gravitational encounters, which often produce tilted or even reversed orbits. A later study reinforced this picture. A team using the Galileo National Telescope detected the Rossiter-McLaughlin effect during a transit of HAT-P67b. This effect appears as a subtle distortion in the star's radial velocity signal when part of its rotating surface is blocked by a transiting planet. By analyzing the shape and strength of that distortion, the team measured the projected spin-orbit angle to be just about 2.2 degrees. With an uncertainty of plus or minus 0.4 degrees. In other words, the alignment is nearly perfect. The planet's orbital plane and the star's equatorial plane are almost identical. as if the planet is still following the original path set by the disk from which it formed billions of years ago. This near-perfect alignment strongly suggests that the planet did not experience a violent past. There were likely no close encounters with other massive planets, no dramatic scattering events, no chaotic rearrangements. Instead, HAT P67b appears to have migrated inward in a much gentler way, gradually drifting closer to its star through the smooth, viscous interaction with the protoplanetary disk. So, whatever made this planet so extreme, it was not the result of a turbulent history. It is the consequence of its present environment. The discovery paper, led by George Joe and colleagues, was published in 2017 in the Astronomical Journal. It reported a radius of about 2.08, 5 times that of Jupiter. It also placed an upper limit on the mass at less than 0.59 Jupiter masses, and a lower limit above 0.056 Jupiter masses. Based on constraints from Roche lobe overflow, and from those values, one conclusion became clear. HAT P67b was among the lowest density gas giants ever identified, a planet with the scale of a giant. But the substance of almost nothing. But there was a problem. The mass was not precisely known. An upper limit is not the same as a true measurement. Saying the planet weighs less than 0.59 times, Jupiter's mass is similar to saying a person weighs less than 200 pounds. They might weigh 190, or they might weigh 80. The difference is enormous. And it changes everything about how we interpret the object. Without an accurate mass, astronomers could not determine whether the planet's atmosphere was stable or actively escaping. They could not confidently model its internal structure, and they could not predict what its future might look like. For nearly 8 years, that uncertainty remained. During that time, multiple teams continued to study the planet's atmosphere, uncovering increasingly unusual and intriguing signals. We will come back to those atmospheric clues shortly. But the more fundamental question, how much this planet actually weighs, remained unresolved. The rapid rotation of its host star continued to limit the effectiveness of traditional radial velocity measurements. Then, in 2025, a breakthrough arrived. A team led by Gavin Wang published a new study using the NEID spectrograph, a next-generation instrument mounted on the WIN 3.5-meter telescope at Kitt Peak National Observatory. They carried out a radial velocity campaign specifically designed to overcome the challenges created by the star's activity. NEID offers extremely high spectral precision. But more importantly, the team developed a refined method to separate the planet's signal from the noise introduced by the star itself. To do this, they first analyzed the star's behavior using both photometric data and spectral indicators. This revealed that the star's rotation period, about 5.40 days, is strikingly close to the planet's orbital period of 4.81 days. This near alignment made the problem even more complex. Signals caused by the star's rotation can overlap with the planet's orbital signal, either mimicking it or obscuring it entirely. In other words, the star itself can create false patterns that look almost identical to the presence of a planet. To address this, the team applied a constrained quasi-periodic Gaussian process, a statistical approach designed to model the correlated noise produced by stellar activity, while isolating the consistent signal of the orbiting planet. They combined multiple sources of data in a single analysis, including archival ground-based photometry, space-based observations from the Transiting Exoplanet Survey satellite, known as TESS, and their new radial velocity measurements from NEID. The result was the first reliable measurement of the planet's mass, about 0.45 times that of Jupiter. With an uncertainty of plus or minus 0.15, combined with a refined radius of roughly 2.14 times Jupiter's size, with a margin of plus or minus 0.025. This led to a calculated density of around 0.061 grams per cubic centimeter. Even with an uncertainty of roughly 33%, that value placed HAT-P67b among the most extreme planets ever measured, the second lowest density hot gas giant known. Only one other confirmed planet falls below the critical threshold where planetary physics suggests such worlds should not survive for long. And that threshold is important, because it helps explain why this planet is so unusual. Research by Daniel Thorngren and collaborators has shown that hot gas giants, with densities below about 0.1 grams per cubic centimeter, exist in a highly unstable regime. At these densities, the planet's gravity becomes too weak to effectively hold onto its atmosphere, especially under the intense energy input from its host star. High-energy ultraviolet radiation from the star ionizes hydrogen and helium in the upper atmosphere, heating it to the point where individual atoms gain enough energy to escape the planet's gravitational pull. At first, this escape can be gradual, a slow loss of particles from the outermost layers over billions of years. But for planets this diffuse, the situation changes dramatically. Once the density drops below that critical threshold, the process no longer remains stable. It becomes runaway. The atmosphere begins to escape faster than it can be replenished. As the planet loses mass, its gravity weakens further, which allows even more gas to escape. That, in turn, reduces the gravity again. This creates a feedback loop. The planet continues to deflate, its atmosphere thinning more and more rapidly, until eventually nothing substantial remains, leaving behind either a stripped core, or in some cases, no planet at all. Theoretical models suggest that this runaway process should strip a planet of its atmosphere in less than 100 million years. And this is where the real puzzle begins. HAT-P67b has a density of just 0.061 grams per cubic centimeter, well below the threshold where such planets are expected to survive. Yet its host star is not young. The system itself is estimated to be more than 1 billion years old. According to those models, the planet should have lost its atmosphere hundreds of millions of years ago. It should no longer exist in its current form. What remains should be either a bare core or nothing at all. And yet, we still observe it, large, inflated, and clearly retaining an atmosphere that, by all expectations, should have disappeared long ago. The study published in 2025 offers a resolution to this paradox, and the answer lies with the star itself. HAT-P67 is not a stable main sequence star. It is a subgiant, a star that has begun to exhaust the hydrogen fuel in its core and is slowly evolving toward the red giant phase during the main sequence lifetime of an F-type star. Its ultraviolet radiation follows a distinct pattern. Early on, when the star is young and magnetically active, its ultraviolet output is high. As it ages and that activity declines, the ultraviolet radiation decreases as well. For most of its lifetime on the main sequence, HAT-P67 likely emitted less ultraviolet radiation than would be required to trigger runaway atmospheric escape from its planet. But that situation is now changing. As the star evolves beyond the main sequence and its luminosity increases, the radiation environment around the planet is shifting rapidly. The amount of extreme ultraviolet radiation reaching the planet is rising as the star expands and becomes brighter. The study led by Wang and colleagues suggests that this destructive phase of atmospheric loss is relatively recent, for more than 1 billion years. The planet may have remained in a delicate balance, inflated by intense radiation, yet still able to retain its atmosphere. Only now, as the star enters its subgiant stage and its radiation profile changes, has the planet crossed into the regime where atmospheric escape accelerates toward the catastrophic outcome predicted by theory. In other words, we are observing HAT P67b at a very narrow and fleeting moment in its lifetime. For most of its existence, it remained inflated yet stable, but now it has crossed into a far more dangerous phase. The star is growing brighter, the atmosphere is steadily escaping, and time is beginning to matter. Current estimates suggest the planet may be tidally disrupted or eventually engulfed by its expanding star within roughly 150 to 500 million years. From a human perspective, that may sound like an immense span of time, but on cosmic scales, it is only a brief interval. The universe itself is nearly 14 billion years old. And even 500 million years represents less than 4% of that total. In a sense, this planet is already in the final chapter of its existence, and we are witnessing it in real time. To understand what this environment truly means, it helps to imagine the conditions at its orbital distance of about 10 million kilometers. The host star, already about 2.6, 5 times the size of our Sun and 12 times more luminous, dominates the sky from the planet's perspective. If you could somehow hover above the cloud tops without being destroyed, the star would not appear as a small disk like our Sun does from Earth. Instead, it would fill a vast portion of the sky, spanning roughly 20 degrees, nearly 40 times wider than the Sun appears to us. On the day side, the planet is exposed to radiation so intense that molecules in the atmosphere are torn apart into individual atoms. Sodium and potassium exist as free atomic vapor. Hydrogen dissociates. Even elements like iron and magnesium may remain in gaseous form under such extreme conditions. The night side, however, presents a very different picture. The planet is likely tidally locked, or close to it, meaning one side always faces the star while the other remains in perpetual darkness. On that far hemisphere, no direct starlight arrives. Temperatures can drop by hundreds, or even more than 1,000 Kelvin, creating one of the most extreme temperature contrasts known among exoplanets. To compensate, powerful atmospheric winds, predicted by circulation models to reach speeds of several kilometers per second, attempt to transport heat from the scorching day side to the cooler night side. These high-speed jet streams circle the planet along the equator, transporting intensely heated gas from the bright, illuminated side toward the darker hemisphere. But this redistribution is far from perfect. The night side remains significantly cooler. At the terminator, the narrow boundary between eternal day and eternal night, temperatures can shift by hundreds of degrees across distances smaller than a continent. Along this thin twilight zone, clouds may form and dissipate in narrow, shifting bands. These sharp temperature contrasts drive powerful atmospheric dynamics, which play a central role in the inflation processes we will explore next. The intensity of radiation striking the day side has another important effect. It sets the planet's equilibrium temperature at around 1,900 Kelvin, placing HATP 67b right at a critical boundary in how astronomers classify planetary atmospheres, below roughly 2,000 Kelvin. Atmospheric chemistry is dominated by molecules such as water vapor, carbon monoxide, and methane. But above that threshold, these molecules begin to break apart through thermal dissociation, and the atmosphere becomes dominated by individual atoms and ions instead. HATP-67b sits directly at this transition. Its day side likely enters this atomic regime, while its night side may still preserve more familiar molecular chemistry. In that sense, the planet is not simply hot, it exists at a chemical tipping point, where its atmosphere changes character depending on which hemisphere you observe. To better understand just how unusual this world is, it helps to place it on the mass-radius diagram, a fundamental tool astronomers use to compare and classify planets. This diagram plots planetary mass along one axis and radius along the other. Every known exoplanet with measured values occupies a point on this chart, and the overall distribution reveals clear patterns. Most gas giants fall within a predictable region. Planets with about 1 Jupiter mass typically have radii between 1 and about 1.2 times that of Jupiter. As planetary mass increases beyond Jupiter, something interesting happens. The radius no longer continues to grow, and in some cases, it even begins to decrease. This occurs because stronger gravity compresses the material more efficiently. This behavior is well understood through the physics of degenerate matter. As more hydrogen and helium are added, the increasing gravitational pressure can compress the existing material faster than the added mass expands it. The result is a limit, where adding more material actually makes the planet smaller rather than larger. The result is that cold gas giants tend to reach a maximum size of about 1 to 1.2 times the radius of Jupiter. But hot Jupiters do not follow this pattern. Intense stellar radiation can inflate their atmospheres, pushing their radii beyond that natural limit and scattering them upward on the diagram. Many of these planets fall between 1.2 and 1.5 Jupiter radii, some extend to 1.7 or 1.8. And a few extreme cases grow beyond 2 Jupiter radii. HATP-67b sits at the very edge of this distribution. Its radius exceeds 2 times that of Jupiter. While its mass remains below half of Jupiter's, it occupies a region of the diagram so sparsely populated that only a handful of planets are found there. And those that do exist in this corner share similar traits. They are intensely irradiated. They orbit very close to their star. They are actively losing mass, and they are not expected to survive for long on cosmic timescales. So the emptiness of this region is not due to a lack of discovery, it is a lack of survivors. The mass-radius diagram also reveals something essential for understanding why this planet is so unusual. For any given radius, there is a range of possible masses depending on composition, temperature, and the level of stellar irradiation. A planet with a radius of 2 Jupiter radii could, in principle, have several times Jupiter's mass, if it is not strongly heated, but under extreme irradiation, that same radius could correspond to a much lower mass, even less than 1 Jupiter mass. However, when the mass drops below roughly half of Jupiter's, while the radius remains above 2 Jupiter radii, the planet enters a regime where standard models can no longer explain its structure. No combination of composition and normal cooling processes can produce such a configuration. Something external must be supplying energy, continuously preventing the planet from contracting. And that source is the host star. The radiation from HATP-67, now about 12 times more luminous than our Sun, and concentrated on a planet just 10 million kilometers away, injects enough energy into the atmosphere to keep the planet expanded far beyond its natural equilibrium size. Exactly how this energy penetrates deep enough to influence the entire structure of the planet is still an open question. But the observation itself is clear. This world is far larger than any cold planet of similar mass could ever be. And the system holds one more detail that adds to its complexity. HAT P67 is not alone. It is part of a binary system. Observations from the Gaia spacecraft have revealed a distant red dwarf companion with about 0.58 times the mass of our Sun and roughly 0.68 times its radius, orbiting the primary F-type subgiant at a distance of around 3,400 astronomical units. That distance is enormous, far too large for the companion star to directly influence the planet's orbit or atmosphere today. But its presence still raises questions about the system's past. Could gravitational effects from this distant companion have played a role in guiding the planet inward billions of years ago? The planet's well-aligned orbit suggests a smooth, disk-driven migration rather than a chaotic history of violent scattering. Even so, the dynamics of a binary system are always more complex than those of a single star. The host star's rapid rotation adds another layer of interest. Spinning at nearly 36 kilometers per second, it completes a rotation in about 5.4 days, remarkably close to the planet's orbital period of 4.81 days. This near synchronization may simply be a coincidence, but it could also point to a deeper physical interaction between the star and the planet. Tidal forces from a close-orbiting massive body can transfer angular momentum to the star, gradually spinning it up or bringing its rotation into alignment with the planet's orbit. Some researchers have also suggested that magnetic interactions between the star and the planet could contribute to this coupling. Although the evidence for such effects remains uncertain, what is not uncertain, however, is the planet's current condition. Multiple independent observations now confirm that HAT P67b is actively breaking apart. The clearest evidence comes from atmospheric transmission spectroscopy, a technique that studies how starlight changes as it passes through a planet's atmosphere during transit. As the planet moves across the face of its star, a thin layer of atmosphere along its edge absorbs specific wavelengths of light. Depending on the elements present, by comparing the star's spectrum during and outside of transit, astronomers can identify the chemical composition of the planet's upper atmosphere. But in the case of HAT P67b, these observations revealed something far more dramatic than just a list of elements. They revealed a planet in the process of losing itself. A team led by Aaron Bello used the Carmine spectrograph at the Calo Alto Observatory and detected signatures of sodium and ionized calcium in the atmosphere. The presence of ionized calcium was particularly striking. This type of signal is usually associated with much hotter planets. Its detection here suggests that the upper atmosphere is more strongly ionized than expected. In addition, the data showed absorption in the hydrogen alpha line and in the helium triplet, both well-known indicators that atmospheric gas is actively escaping into space. A separate observing campaign, led by Michael Guillot Santiago, used the Habitable Zone Planet Finder spectrograph on the Hobby Eberly telescope and revealed something even more striking. Over a total of 13.8 hours of observation, spread across 39 nights, the team was able to sample nearly the entire orbit of the planet. During transit, they detected up to 10% excess absorption in the helium triplet line, but the signal did not appear only during the transit itself. Additional absorption was detected even before the planet began crossing in front of the star, extending far ahead of it, out to nearly 130 planetary radii. That is an enormous structure, a stream of escaping gas stretching so far ahead in the planet's orbit that, if it were visible, it would dwarf the planet itself by more than 2 orders of magnitude. This leading tail forms because the planet has expanded beyond its Roche lobe, the teardrop-shaped region where material remains gravitationally bound to the planet rather than to the star. Once the atmosphere extends beyond that boundary, gas begins to spill outward and fall toward the star. Because this escaping material originates on the day side, the side facing the star. And because orbital motion carries it forward, the outflow does not trail behind the planet as one might expect. Instead, it forms a stream that leads the planet along its orbit. The helium absorption data showed Doppler velocity patterns consistent with this scenario. The gas was moving in the reference frame of the star, not the planet, exactly as predicted by models of Roche-Lobe overflow. The same study also detected a much fainter trailing tail behind the planet, along with variations in the helium signal from one transit to another, suggesting a complex interaction between the stellar wind and the escaping planetary atmosphere, using one-dimensional Parker wind models. The team estimated the mass loss rate to be on the order of 10 to the power of 13 grams per second, though with significant uncertainty due to the poorly constrained ultraviolet output of the host star. In more familiar terms, that corresponds to roughly 10 million metric tons of atmosphere escaping every second. A third research group, led by Cecilia and collaborators, analyzed average spectra taken after transits and found a similarly strong helium absorption signature. From this, they inferred that the planet's effective radius, when observed in helium wavelengths, expands to nearly 6 times the radius of Jupiter, and yet, the physical planet itself is only a little over 2 Jupiter radii wide, but the cloud of escaping gas surrounding the planet is so vast and so extended that when observed through helium absorption, the planet appears to expand to nearly 6 times the width of Jupiter, the core. If a distinct one even exists within such a diffuse structure, is enveloped by layers of gas that stretch far beyond what we would normally call the planet's surface, gradually thinning into a stream that flows outward toward the star. This is not a stable world with a thin atmosphere slowly leaking away. It is a planet whose outer layers are actively spilling into space in real time, forming enormous structures that extend across millions of kilometers, and even altering how large the planet appears depending on the wavelength we use to observe it. At this point, the boundary between the planet and its escaping atmosphere becomes difficult to define. Where does the planet truly end? And where does the outflow begin? There is no clear edge, only a gradual transition, from bound gas to escaping stream, and eventually into the surrounding stellar wind. Taken together, these observations describe a world in an extreme state, a planet that is among the largest ever measured by radius, yet also one of the least substantial in terms of mass. A world whose atmosphere is being stripped away on timescales that, in cosmic terms, are remarkably short. And all of this is happening while its host star continues to evolve, growing brighter, expanding outward, and intensifying the conditions around an already fragile companion. And this leads to a broader question. If planets with such low densities are expected to lose their atmospheres within 100 million years, and HAT P67b has only recently entered this phase, then how many similar worlds have already disappeared? How many planets like this once existed, briefly, vast, luminous, and unusual, before fading away or being consumed by their stars? The scarcity of objects in this region of the mass-radius diagram is not simply a matter of rarity, it is evidence of loss. We observe so few because most of them are already gone. What remains to be understood is how a planet reaches such an inflated state in the first place, the mechanisms that inject energy into close-orbiting gas giants, and the physics that determines how deeply that energy penetrates. The interaction between inflation, atmospheric escape, and stellar evolution forms a complex system that astronomers are still working to unravel. And that brings us to the next step. looking inside the planet itself. To understand what it truly means for a world to become this inflated, and to see the direct evidence that HAT P67b is not just unusually large, but actively coming apart, to understand how HAT P67b became what it is, we need to set aside many of our usual intuitions about how planets behave. Not because the laws of physics are different, they remain the same everywhere, but because the environment this planet exists in is so extreme that familiar physics begins to produce unfamiliar outcomes. A gas giant in the cold, outer regions of a planetary system is typically stable and well-behaved. But a gas giant orbiting just 10 million kilometers from a luminous subgiant star is something entirely different. It is more like a pressure system pushed beyond its limits, with energy continuously building beneath the surface. So it helps to return to the basics. What determines the size of a gas giant for a cold, isolated planet? The answer is relatively simple. Its radius depends primarily on two factors: its mass, meaning how much hydrogen, helium, and heavier elements it contains, and its age, meaning how long it has had to cool and contract since it formed. Gas giants begin their lives extremely hot. The process of formation releases gravitational energy, heating the material to thousands of degrees. Over time, that heat radiates away into space. The interior cools, pressure decreases, and the planet gradually shrinks. Given enough time, a gas giant of a particular mass and composition will settle into a stable size, an equilibrium determined by the balance between gravity pulling inward and the pressure of degenerate electrons resisting compression. This process unfolds slowly, over billions of years. Jupiter, at around 4.5 billion years old, has contracted to a radius just over that of one Jupiter radius, equivalent to about 11.2 Earth radii. Models suggest that early in its history, Jupiter may have been 30 to 40% larger, and that it will continue to contract very gradually over the billions of years ahead. For cold gas giants, this relationship between mass, I, and radius is clean and predictable. If you know a planet's mass and age, you can estimate its size with remarkable accuracy. But now, change a single variable, move that planet closer to its star. When a gas giant orbits within just a few hundredths of an astronomical unit from a bright star, its entire energy balance is transformed. The planet is no longer cooling freely into space. Instead, one hemisphere is continuously exposed to intense radiation, heating the atmosphere to temperatures exceeding 1,000 Kelvin. And this incoming energy does more than simply warm the outer layers. It begins to reshape the entire thermal structure of the planet. And through a complex chain of physical processes, ones that scientists have spent decades trying to fully understand, this incoming energy can inflate the planet far beyond what its mass and age would normally allow. The central question, the one that has driven countless studies and ongoing debates, is surprisingly simple. How does energy from the star travel from the outer atmosphere down into the deep interior of the planet? Because that is what must happen. Heating only the outer atmosphere is not enough to significantly increase the planet's size. The visible atmosphere represents only a tiny fraction of the planet's total mass. To expand the entire structure, energy has to reach much deeper, into regions where pressures reach hundreds or even thousands of bars, where most of the planet's material is located. Only by warming those deeper layers can the planet's overall density decrease enough for it to expand. If the atmosphere simply absorbed energy and radiated it back into space, the deeper interior would remain relatively cool, and the planet would stay close to its expected size. In that case, The atmosphere would be hot, the interior would be cool, and the radius would remain normal. But observations tell a different story. Hot Jupiters are consistently larger than this simple model predicts. Something is carrying energy downward from the intensely heated atmosphere into the deeper interior, and doing so efficiently enough to keep the planet inflated over long periods of time. Several mechanisms have been proposed to explain how this energy transport might occur. Each offers part of the answer, but none fully explains the entire picture on its own. The current understanding is that multiple processes may be working together, with their relative importance varying depending on the planet's mass, temperature, orbit, and magnetic field. One of the most widely discussed mechanisms is known as ohmic dissipation. The idea begins with the intense radiation heating the upper atmosphere of a close-in gas giant to the point where elements like sodium and potassium become partially ionized. This creates a layer of gas that can conduct electricity. At the same time, strong winds, driven by the temperature difference between the hot day side and the cooler night side, move this ionized gas across the planet's magnetic field. When a conductive fluid moves through a magnetic field, it generates electrical currents. These currents then travel into deeper, more resistive layers of the atmosphere, where they dissipate as heat, similar to how an electric wire warms up when current flows through it. The heat generated by these electrical currents is deposited into the planet's interior, slowing its natural contraction and helping to keep it inflated. Ohmic dissipation is particularly appealing because it creates a direct link between stellar irradiation and planetary size. A hotter atmosphere leads to greater ionization, which produces stronger electrical current, and in turn delivers more heat into the interior. This aligns well with observations, where planets receiving more intense radiation tend to be more inflated. Large-scale studies by Thorngren and Fortney found that the heating efficiency required to match observed planet sizes closely follows what the ohmic dissipation model predicts. Interestingly, the model also suggests a decline in efficiency at extremely high temperatures. When the atmosphere becomes too highly ionized, it turns overly conductive, allowing currents to short-circuit before they can carry energy deep enough to significantly affect the planet's structure. However, this mechanism is not without its limitations. Some calculations indicate that the total energy available through ohmic dissipation may not be enough to explain the most extreme cases of inflation. In addition, the energy tends to be deposited relatively close to the upper layers, near the boundary between radiative and convective zones, rather than deep within the interior. A study published in 2025 provided further insight, suggesting that inflation in hot Jupiters is largely driven by shallow heating. In these models, the intrinsic energy flow from the deep interior is reduced by as much as 95 to 97% compared to earlier assumptions where heating was thought to occur at the core. This supports the idea that mechanisms like ohmic dissipation play a dominant role, but also indicates that the energy may not penetrate as deeply as once believed. A second possible mechanism is tidal heating. When a planet orbits close to its star on a slightly elliptical path, the strength of the star's gravitational pull changes over the course of each orbit. This variation causes the planet's interior to flex, generating friction and heat, much like the process responsible for the intense volcanic activity on Jupiter's moon Io. Tidal heating has the advantage of depositing energy directly into the deep interior, making it potentially very effective at inflating a planet. But there is a complication. This process requires the orbit to remain somewhat eccentric. Most hot Jupiters, especially those on very short orbits, have had their paths circularized over time by tidal forces. This circularization tends to happen relatively quickly compared to the age of the system. By the time we observe these planets, their orbits are usually close to perfectly circular, leaving little opportunity for ongoing tidal heating. For HAT P67b, the orbit appears to be nearly circular, which limits how much tidal heating can contribute to its current state. That said, tidal effects may still have played a role earlier in its history, before the orbit settled into its present shape. A third mechanism involves the transport of potential temperature through atmospheric circulation. Studies of hot Jupiter atmospheres have shown that the powerful winds moving heat from the day side to the night side do more than simply redistribute energy across the surface. These circulation patterns can push atmospheric gas downward on the night side, carrying energy from the hot upper layers into the deeper interior. In doing so, they effectively shift the internal temperature structure onto a hotter profile than what simpler, one-dimensional models would predict. That means the deeper layers of the planet remain warmer than expected, and a warmer interior naturally leads to a more expanded structure. The planet swells. This mechanism is particularly appealing because it does not rely on anything unusual. No strong magnetic effects, no orbital eccentricity, just atmospheric circulation. Something that any strongly irradiated planet would develop on its own. However, modeling this process accurately requires complex three-dimensional simulations. And different research groups have reached different conclusions about how much inflation it can actually produce. The debate is still ongoing. For HAT P67b, the level of inflation is so extreme that it is likely not explained by a single mechanism alone. Its mass, around 0.45 times that of Jupiter, places it within a range where planets are especially sensitive to stellar heating. Studies have shown that planets between roughly 0.37 and 1 Jupiter mass respond most strongly to irradiation. Below this range, planets do not have enough atmospheric mass to expand significantly. Above it, stronger gravity compresses the material more effectively, resisting expansion. HAT P67b sits directly within this narrow window where even a modest amount of additional internal heating can produce a dramatic increase in size, simply because the planet's gravity is too weak to counteract it. This leads to one of the more counterintuitive aspects of planetary physics. Adding mass to a planet does not always make it larger. Beyond a certain point, typically a few times the mass of Jupiter for cold planets, adding more material actually makes the planet smaller. The increased gravity compresses the existing layers more than the new material can expand them. So the relationship between mass and radius is not a simple upward trend. It reaches a peak, and then begins to decline. The largest planets, in terms of radius, are not the most massive ones, but the most inflated ones. Worlds with moderate mass, exposed to extreme heating conditions, and HAT P67b represents one of the most extreme examples of this effect. A planet with less than half the mass of Jupiter, expanded by intense stellar radiation to more than twice Jupiter's size. The ratio between its actual radius and what models predict for a cold planet of the same mass is remarkable. A cold, isolated planet with about 0.45 times the mass of Jupiter would be expected to have a radius close to 1 Jupiter radius, perhaps even slightly smaller. But HAT P67b is more than twice that size. In other words, something has expanded this planet far beyond its natural state, spreading the same amount of material across a volume nearly 10 times larger than expected. To understand what this kind of inflation does to the interior, it helps to compare it with Jupiter. Despite its size, Jupiter has a surprisingly structured interior. Beneath the visible cloud tops, pressure rises rapidly with depth. Within just a few thousand kilometers, hydrogen transitions from a gas into a dense liquid state. Deeper still, at pressures above roughly 2 million atmospheres, hydrogen undergoes a transformation into metallic hydrogen, a phase where electrons are no longer bound to individual atoms, but move freely. Similar to those in a metal, this layer extends across tens of thousands of kilometers and is responsible for generating Jupiter's powerful magnetic field. At the center, there is likely a core made of heavier elements. Rock and ice compressed to extreme densities, perhaps 10 to 20 times denser than water. Pressures there can reach around 40 million atmospheres, with temperatures exceeding 20,000 Kelvin. Now imagine taking that structure and spreading less than half of Jupiter's mass across a volume 10 times larger. The entire internal profile would change. Pressure would drop dramatically at every level. Each layer would become more diffuse. The transition from molecular to metallic hydrogen, which depends on very high pressure, might occur much deeper within the planet, or be far less pronounced overall. Any central core, if present, would sit within a far more extended and diluted envelope. Its influence spread thin across an enormous volume. The pressure gradient from the outer layers to the center would be much more gradual than in Jupiter. Instead of sharply defined layers with clear transitions, HAT-P67b likely has a smoother, more uniform internal structure, with density increasing slowly from the near vacuum of its outer atmosphere toward whatever concentration of heavier material remains at its core. There are no sharp phase transitions here. No dense shell of metallic hydrogen. No extreme core conditions approaching those found inside stars. Instead, the structure is smooth, a gradual transition from something substantial to almost nothing, spread across a diameter more than twice that of any planet in our solar system. This comparison reveals something that a simple density value cannot fully capture. Jupiter is dense because its material is compressed under immense gravity. HAT-P67b is diffuse because its material has been stretched outward. Both planets are composed primarily of hydrogen and helium, with small amounts of heavier elements, but Jupiter is tightly packed into a layered structure by its own gravity. While HAT-P67b has been expanded by external energy into something more like a warm and tenuous cloud. The result is a density that barely resembles what we typically think of as matter, about 0.061 grams per cubic centimeter. In more familiar terms, that is roughly 1/16th the density of water and about 1/22nd the density of Jupiter. If it was somehow possible to place HAT-P67b into a cosmic ocean large enough to contain it, it would float extremely high, with only a small fraction of its volume submerged. But even that analogy begins to break down, because at such low density, the planet does not behave like a solid or even a liquid. It is better described as an extended envelope of gas, a diffuse cloud of hydrogen and helium with no sharply defined surface, gradually fading from denser inner regions into the near vacuum of space. And this is where the strangeness becomes most apparent. At what point does a planet stop being a planet and begin to resemble a cloud? For a world like Jupiter, the distinction is clear. Density rises quickly with depth. There are defined layers, transition, and a strong sense of structure held together by immense gravitational pressure. But for HAT-P67b, that boundary becomes much less distinct. The material is spread so thinly across such a vast volume that the transition from planet to space is not sharp, but gradual, almost conceptual. It is worth pausing here to recognize just how rare a planet like this truly is. Even among the already uncommon class of inflated hot giants, the study by Wang and colleagues in 2025 notes that only a handful of confirmed planets fall below the density threshold of 0.1 grams per cubic centimeter. The exact members of this group may change as measurements improve, but their shared characteristics are clear. They all orbit their stars in less than about a week, and they are all exposed to extreme levels of stellar irradiation. All of these planets are thought to be on unstable evolutionary paths, destined to lose their atmospheres on relatively short cosmic timescales. But even within this already rare group, HATP 67b stands out. Its density, around 0.061 grams per cubic centimeter, is lower than most of its closest counterparts. And its mass, less than half that of Jupiter, is the smallest among them. The others, at least, retain masses closer to Jupiter's. HATP 67b reaches its enormous size with even less material, making its inflation more extreme and far more difficult for any single theoretical model to explain. It is not just another inflated planet. It is the one that pushes the entire category to its limits. And this extreme diffuseness is not just a conceptual detail. It has real physical consequences. A lower density means weaker surface gravity. And weaker gravity allows the atmosphere to extend much farther outward relative to the planet's size. One way to describe this is through the scale height, the vertical distance over which atmospheric pressure drops by a factor of about 2.7. This scale height depends on temperature and surface gravity for HATP 67b. The combination of very high temperature and low gravity produces a scale height of roughly 800 kilometers. For comparison, Earth's atmospheric scale height is about 8.5 kilometers. That means the atmosphere of HATP 67b extends about 100 times farther in absolute terms, and even when scaled to the planet's size, it is still several times more extended. This unusually large scale height is exactly what makes the planet such an ideal target for atmospheric studies. In transmission spectroscopy, the strength of absorption features depends on how much of the star's light passes through the planet's atmosphere. A more extended atmosphere creates stronger, more detectable signals. That is why multiple research teams have been able to identify a wide range of atmospheric signatures, including clear evidence of gas escaping into space, even at a distance of around 1,200 light-years. The planet's atmosphere is so expanded that it leaves a measurable imprint on the starlight passing through it. But this same characteristic that makes the planet easy to study also makes it fragile. And this is where the story begins to shift, from inflation to destruction. A planet's Roche lobe defines the region where material remains gravitationally bound to it. Beyond this boundary, gas is no longer held by the planet and instead falls under the influence of the host star. The size of this region depends on the planet's mass, the star's mass, and the distance between them. For HATP 67b, the combination of low planetary mass, a relatively massive star, and a very close orbit creates a Roche lobe that is unusually small compared to the planet's inflated size. The planet not only fills its Roche lobe, it exceeds it. Its expanded atmosphere stretches beyond the boundary where material can remain gravitationally bound, and once gas crosses that threshold, it does not linger. It begins to stream outward, pulled toward the star along paths shaped by both gravitational forces and the motion of the orbit itself. To picture this, imagine a water balloon being forced through a narrow opening. The Roche lobe defines that opening a teardrop-shaped boundary with its narrowest point, known as the first Lagrange point, directed toward the star. Gas heated in the upper atmosphere expands beyond this point and begins to spill through that narrow gravitational channel. But unlike water flowing in a straight stream, this gas exists within a rotating system. The planet is moving around its star at speeds of tens of kilometers per second. And the escaping material carries much of that motion with it. As the gas leaves the planet and enters the star's gravitational domain, its path is curved by the Coriolis effect. Gas escaping from the day side, the side facing the star, is swept forward along the orbit, forming a stream that leads the planet, almost like the bow wave of a ship cutting through water. Gas escaping from the opposite side follows a different path, curving backward into a much fainter trailing tail. The leading stream appears brighter and denser, because the strongest outflow originates from the intensely heated day side. The result is a planet surrounded by an uneven envelope of escaping gas, with a prominent leading arm stretching far ahead, and a more diffuse tail trailing behind. This asymmetric structure is exactly what the helium observations revealed. The excess absorption detected even before the planet begins, its transit is the signature of that leading stream passing in front of the star ahead of the planet itself. So the gas is not dispersing randomly into space. It is being shaped by orbital motion into a coherent, structured flow, a stream with form, direction, and velocity, a visible trace of a world slowly unraveling. The estimated mass loss rate, based on these helium observations, is on the order of 10 million metric tons per second. To put that into perspective, in just a single Earth day, the planet loses roughly 800 trillion kilograms of its atmosphere over the course of a single year. The total mass lost exceeds the combined mass of every building, vehicle, ship, and structure humanity has ever created many times over. The loss is constant, relentless, and visible across every timescale we choose to examine. It sounds catastrophic, and it is, but perspective matters. P67b has a total mass of roughly 0.45 times that of Jupiter, equivalent to about 8.5 times 10 to the power of 29 grams. At its current rate of atmospheric escape, it would take on the order of 2.7 billion years to completely lose its mass. But that is not what will happen. The runaway escape process appears to have begun only recently, triggered by the star's increasing luminosity as it evolves beyond the main sequence. And before the planet has time to fully evaporate, another process will intervene. The star itself is expanding within roughly 150 to 500 million years. The star will grow large enough to either tidally disrupt the planet, stretching it beyond structural stability, or engulf it entirely. So the planet's fate is sealed from both directions at once. It is losing its atmosphere from above, driven by intense radiation, while at the same time, the star is expanding outward from below, closing in on its orbit. Whether the atmosphere is stripped away first, or the star consumes the planet first, depends on details we cannot yet fully constrain. But the outcome does not change. Within a few 100 million years, P67b will no longer exist as a recognizable planet, and in this context, the spectroscopic signals we discussed earlier take on a deeper meaning. The sodium and ionized calcium detected are not simply passive components of an atmosphere. They are signatures of a system being pushed far beyond equilibrium. The presence of ionized calcium, in particular, suggests temperatures much higher than would be expected from radiation alone. The most likely explanation is that the escaping outflow itself contributes additional heating as gas accelerates outward, passing through and beyond the sonic point. Thermal energy is converted into motion, while extreme ultraviolet radiation continues to energize the flow. This creates a thermosphere heated to nearly 9,900 Kelvin, almost 5 times hotter than the planet's equilibrium temperature. This layer is not static. It acts as the launch region for a transonic planetary wind. The physics is similar to the solar wind from our own sun. In the sun's corona, gas heated to extreme temperatures expands outward, accelerates beyond the speed of sound, and flows into interplanetary space. HAP-P67b is doing something similar, but instead of a star, it is a planet generating the outflow. Gas in the lower thermosphere rises slowly, driven by pressure from below. As it moves outward and pressure drops, it accelerates, crossing the sonic point and continuing to gain speed as it expands beyond the Roche lobe into near vacuum. From there, the material feeds into the leading and trailing streams we described earlier, continuously replenishing a vast, structured outflow that reshapes how the planet appears depending on how we observe it. This wavelength dependence is one of the most striking consequences of the escape. Invisible light. The planet appears with a radius of about 2.14 times that of Jupiter, representing the level where the atmosphere becomes opaque enough to block starlight. But in the narrow wavelength of the helium triplet, a different picture emerges. The absorption begins even before the planet itself crosses the star, revealing the extended leading stream already passing in front. It continues even after the planet itself has passed, as the trailing stream follows behind, extending the signal beyond the transit. In helium light, the effective radius reaches nearly 6 times that of Jupiter, almost 3 times larger than what we see in visible wavelengths. So the planet you observe depends entirely on how you choose to look at it. In white light, it appears as an unusually large world, but in helium light, it becomes something else entirely, a vast, diffuse cloud, with a planet somewhere hidden within it. All of these observations point toward a single, consistent conclusion. HAP-P67b is not simply a large planet. It is not only an inflated one, it is a planet in the process of coming apart. Its atmosphere is escaping into space at a rate of millions of tons per second. Its apparent size changes depending on the wavelength of observation. Its Roche lobe is overfilled. Its host star is growing brighter and expanding toward it. Its density is so low that the word planet begins to feel inadequate. And yet, it exists. It has been observed by multiple independent teams, using different instruments, across multiple wavelengths. Its mass, radius, density, atmospheric composition, escape rate, tail structure, and orbital dynamics are all measured and documented in peer-reviewed studies. This is not a theoretical curiosity. It is not a simulation. It is a confirmed world, catalogued in the NASA Exoplanet Archive, and listed among the largest known planets by radius. So the question is no longer how large a planet can become. The deeper question is this: what does the word planet actually mean? When the object in question is less dense than a marshmallow, actively losing its atmosphere into a stream stretching more than 130 times its own size, and destined to disappear within a few 100 million years. That question is where this story truly ends. Because what follows is not just about HAP-P67b, but about what its existence implies, about the fragility of structures on a cosmic scale, and about the possibility that the largest things in the universe are not the most powerful, but the most temporary. There is a moment in every scientific journey when the facts stop feeling like isolated data points and begin to reshape how we see the universe. Not because the data has changed, but because our understanding has finally caught up to what it has been telling us all along. This is that moment. Because the unsettling truth about HAT P67b is not its size, not the helium tail, not the rate at which it is losing mass, or the fact that its star is dying. It is what all of these things, taken together, suggest. So we return to the title. The largest planet in the universe. Is that really true? The honest answer is more complicated. Here is what we can say with confidence. HAT P67b is among the largest planets ever measured by radius. The NASA Exoplanet Archive, the most comprehensive catalogue of confirmed exoplanets, lists its size at about 2.14 times the radius of Jupiter. Out of more than 5,700 confirmed exoplanets with measured radii, this places it at, or very near, the extreme upper edge of what we have observed. The study published in 2025 by Wang and collaborators refers to it directly as the largest known hot giant planet. In terms of sheer physical size, it stands among the widest planets ever confirmed by observation. But calling it the largest planet in the universe comes with important caveats, the kind that careful science requires us to acknowledge. First, our observations represent only a tiny fraction of what actually exists. The Milky Way alone likely contains hundreds of billions of planets, and the observable universe holds on the order of 2 trillion galaxies. Compared to that, the roughly 5,700 confirmed exoplanets we have catalogued so far represent only an infinitesimal sample, somewhere beyond our current reach. There may be planets even larger than this one. Any claim of the largest reflects the limits of our observations, not the limits of nature itself. Second, measurements of planetary radius are not absolute. They depend on how well we understand the host star. HAT P67b's size is determined relative to the radius of its star. If that stellar value is revised, the planet's size shifts with it. The current measurement is robust. But science is always evolving. Future observations may refine it further. Third, the boundary between planets and brown dwarfs is not perfectly defined. Brown dwarfs occupy the space between planets and stars, too massive to be planets, but not massive enough to sustain stable hydrogen fusion. The conventional dividing line lies at around 13 times the mass of Jupiter, where deuterium fusion becomes possible, but objects near this boundary can sometimes have radii comparable to, or even larger than, HAT P67b, depending on their age and temperature. Whether those objects are classified as planets or failed stars is, to some extent, a matter of definition. If we include young, inflated brown dwarfs, the picture becomes less clear. What we can say with confidence is this. Among confirmed objects that are clearly planetary in mass, HAT P67b is one of the largest ever measured, and it reaches that size not by accumulating more material, not by being the most massive or the most gravitationally dominant, but by being inflated to an extreme that stretches the very definition of what a planet can be. And that is the real story here. Not a record, but a revelation. Think for a moment about what the word planet usually means. It suggests a world, a place, something with a boundary, with structure, with substance, even gas giant. Despite lacking solid surfaces, feel like places in our imagination. Jupiter has bands, Saturn has rings, Neptune has storm. They have identity. They feel cohesive, contained, almost tangible, HAT P67b quietly dismantles that intuition. Because when we strip away the terminology and describe it in simple physical terms, what remains is something very different. It is a collection of hydrogen and helium gas, less massive than Jupiter, spread across a volume roughly 10 times larger. Its density is so low that the gas near its outer layers, if we can even define a surface at all, is thinner than the conditions inside many laboratory vacuum chambers on Earth. It has no clearly defined edge. Its atmosphere does not end at a boundary. It simply fades outward, gradually blending into the escaping stream of gas that stretches more than 130 planetary radii ahead of it along its orbit. At certain wavelengths, the planet appears nearly 6 times wider than Jupiter. Not because the planet itself is that large, but because the surrounding cloud of escaping gas absorbs starlight far beyond the region where gravity can still hold it in place. So where exactly is the planet? Where does the object end and the process begin? These are not abstract questions. They are real physical ambiguities that HAT P67b forces us to confront. For a rocky world like Earth, the boundary is obvious. The surface marks the edge. For Jupiter, the answer is less precise, but still workable. The visible cloud tops provide a reasonable reference, even though the atmosphere extends beyond them. But for HAT P67b, that clarity disappears. What we are looking at is not a sharply defined object, but a region of higher density embedded within a much larger, more diffuse outflow, a concentration within a gradient rather than a solid, self-contained world in a very real sense. It is not a thing, but a transition. This may sound philosophical, but it has direct scientific applications. When astronomers measure the radius of a transiting planet, they are not measuring a solid edge. They are identifying the altitude at which the atmosphere becomes opaque enough to block a detectable fraction of starlight. For compact planets, this measurement aligns closely with the physical boundary. But for HAT P67b, it corresponds to the outer layers of a vastly extended atmosphere, some of which may no longer even be gravitationally bound. So the number we call the planet's radius is not the edge of a world. It is the edge of visibility. In one sense, the planet extends far beyond that boundary. In another, it is much smaller if we consider only the material that remains truly bound and cohesive. Even the planet's mass carries this ambiguity. When we say it has about 0.45 times the mass of Jupiter, we are describing its current gravitational influence. But that mass includes material that is actively escaping. It is not constant. It is changing in real time at a rate of roughly 10 million metric tons per second. The mass we measure today is not the mass it had 1 million years ago, and it will not be the mass it has 1 million years from now. This is not a stable object. It is a moment within a process, and that is what makes it so unusual. We are used to thinking of planets as enduring features of their systems. Earth has existed for billions of years. Jupiter as well, even on astronomical timescales. They feel permanent. They will survive long after the Sun leaves the main sequence. HAT P67b will not. Its existence as a recognizable planet is temporary. Not temporary on the scale of the universe, but temporary even within the lifespan of a star. Within roughly 150 to 500 million years, this world will either lose its atmosphere entirely through continuous escape, or be swallowed as its host star expands into a red giant. Either outcome leads to the same conclusion. The object we now call HAT P67b will no longer exist in any familiar form within a timescale that is short compared to the age of its own system. which already exceeds 1 billion years. For most of its life, the planet existed in a fragile balance. For over 1 billion years, it remained inflated, yet intact. Its atmosphere was heated and extended, but not escaping fast enough to destroy it. During that long period, the host star, still in its main sequence phase, did not emit enough extreme ultraviolet radiation to trigger runaway mass loss. The planet existed in a kind of unstable equilibrium, like something stretched close to its limit. But still holding together, then the star began to change. As hydrogen in its core became depleted, the star evolved, growing brighter and expanding as it moved into the subgiant phase. And with that change, the environment surrounding the planet shifted. The increase in luminosity pushed the radiation level past a critical threshold. Atmospheric escape accelerated beyond what the planet could sustain. The slow leak became something irreversible, and unlike a balloon, this world cannot recover. The same energy that once kept it inflated is now driving it toward destruction. This is the paradox at the heart of HATP-67b. The very condition that made it extraordinary is the same condition that is ending it. It is enormous because of its star, and it is dying because of that same star. Its defining feature, its immense size, is not a sign of strength, but a symptom of collapse. And this points to something deeper about the nature of extremes in the universe. The most extreme objects are rarely long-lived. The most massive stars burn through their fuel in just a few million years. The brightest quasars mark brief episodes of intense accretion around supermassive black holes. The most energetic events, supernovae, gamma-ray bursts, last only moments on cosmic timescales. Nature can create extremes, but it does not sustain them. To exist at the edge is to exist briefly. And HATP-67b follows that pattern. It is extreme in size, extreme in how little mass supports that size, extreme in how rapidly it is losing itself. And like all extremes, it is temporary. The universe has created a planet at the very edge of what physics will allow. And the cost of existing at that edge is time, a lifespan measured not in billions of years, but only in hundreds of millions. Among the more than 5,700 confirmed exoplanets, objects as extreme as HATP-67b are extraordinarily rare. Not because the conditions needed to form them are impossible, but because those same conditions ensure they do not last. We observe so few worlds in this region of the mass radius diagram, not due to a lack of formation, but because they do not remain there long enough to be commonly seen. And that rarity carries a deeper implication. For every HATP-67b we can observe today, there may have been dozens, perhaps hundreds, of similar planets that once existed in this same extreme state, only to vanish, stripped of their atmospheres, consumed by their stars, reduced to something smaller, or erased entirely. The mass radius diagram is not a fixed map. It is a snapshot, capturing a population in motion. Planets drift into this extreme regime, remain there briefly, and then disappear. What we are seeing are not the rule, but the survivors. The few that still exist within the narrow window of time in which we are able to observe them. And there is something quietly haunting about that. The largest planet we have found is not a monument. It is something already in the process of becoming a memory. It does not sit at the top of a hierarchy, ruling over smaller worlds. It is unraveling, losing itself to space, being consumed by the same star that made it extraordinary. This is not a king on a throne. This is a king in decline. But that sense of loss, that is human. The universe does not mourn. The universe transforms. The gas escaping from HATP-67b does not disappear. It flows toward the star. where some of it will be absorbed into the stellar envelope. Some will be carried away by stellar winds, drifting into interstellar space. Over time, that material will mix with gas and dust throughout the galaxy, becoming part of the raw ingredients from which new stars and new planets will form. The atoms that make up this planet, hydrogen from the beginning of the universe, helium from its earliest moments, will not be lost. They will be reused. The planet ends, the matter continues, and the cycle goes on. From this perspective, destruction is not an exception in the universe, it is part of the process. Planetary systems are not static, they are dynamic. Evolving environments where worlds form, migrate, interact, expand, collapse, and disappear over timescales far beyond human experience. And sometimes, the most extraordinary worlds are the ones that exist only briefly. The quiet stability of our own solar system, where 8 planets have moved in nearly unchanged orbits for more than 4.5 billion years, is not the universal pattern. It is only one possible outcome among many. Elsewhere, planetary systems can be far more chaotic, more dynamic, and far less permanent. HAT P67b exists in one of those environments, a massive, rapidly rotating star that is already evolving, a planet orbiting extremely close, inflated beyond normal limits, and actively losing its atmosphere, and far away, a binary companion that may have influenced the system's early history. This is not a system in equilibrium. It is a system in transition, shifting from one state to another. And the planet is the most visible casualty of that transformation. Astronomers continue to study HAT P67b precisely because it sits at this extreme. Observations from the Hubble Space Telescope are planned or already underway to examine its escaping atmosphere in greater detail. The extended helium tail provides a natural laboratory for studying hydrodynamic outflows, a process believed to have shaped the overall distribution of planets across the galaxy. For example, the so-called radius valley, the observed gap between planets around 1.5 and 2 times the size of Earth, is thought to be the result of atmospheric escape. Smaller planets lose their gaseous envelopes, leaving behind exposed rocky cores. HAT P67b represents that same process, but operating on a much larger scale. Instead of a small sub-Neptune, we are watching a gas giant undergo atmospheric loss. Driven by the intense environment of a close orbit around an evolving star, understanding how this planet loses its atmosphere helps refine models that apply across all types of planets, across different masses, temperatures, and orbital distances. The rate of mass loss, the temperature of the outflow, the shape of the leading and trailing streams, the interaction with stellar winds. Each of these provides critical data. Every survey that counts how many planets exist at different sizes and distances, in effect, counting the survivors of atmospheric escape. And HAT P67b helps us understand those that did not survive. At the same time, the planet challenges our theoretical understanding of inflation itself. With a radius greater than 2 Jupiter radii and a mass below half of Jupiter's, it occupies a regime where standard models require significant additional heating to explain its size. Which mechanisms are responsible, whether ohmic dissipation, atmospheric circulation, tidal effects, or something not yet fully understood, remains an open question. HAT P67b becomes a test case at the extreme edge. Any successful theory of hot Jupiter inflation must be able to reproduce a world like this, without contradicting other observations. If a model cannot produce a planet of 2.14 Jupiter radii at only 0.45 Jupiter masses under these conditions, then that model is incomplete. And this leads us to the deepest layer of the story, the part that exists beneath the measurements, beneath the equations, beneath the models. The part that turns this from a scientific explanation into something that changes how you look at the universe itself. When you look up at the night sky, you are not just seeing distant light. You are looking into a universe capable of creating things that do not simply scale up from what you already know, but things that feel entirely unfamiliar. Not new laws of physics. The same rules you learned still apply, but under different conditions. Those rules can produce outcomes that feel almost impossible. A planet wider than 2 Jupiters, yet with less than half its mass. A world lighter than anything your intuition would accept. A structure so diffuse that it is slowly dissolving into space, leaving behind a faint, extended trail detectable from over 1,200 light-years away. An object so spread out that the line between the planet and the surrounding void is no longer clear, not a boundary, but a fade. At that point, the idea of a planet begins to lose its meaning. This is no longer a place in the way we usually imagine, not a destination, not a surface, not even a clearly defined object. It is closer to a process, something in transition, something that exists only temporarily in a particular state before becoming something else. This is what happens when physics is pushed to its limits. Not disorder, not chaos, but structure stretched so far that it no longer fits the categories we created to describe it. By definition, HAP-P67b is a planet. It orbits a star. Its mass is below the threshold required for fusion. It passes in front of its star. It has an atmosphere. It meets every formal criterion. And yet, something about it resists that label. Because what we are looking at does not behave like a world. It behaves like a temporary concentration of gas barely held together, slowly dispersing, a form that only just qualifies as a planet, and only for a limited time. It is not enduring. It is not stable. It is not meant to last. And somehow, that is what makes it extraordinary. Not in spite of its fragility, but because of it. The universe does not need to create objects like this. It could produce only stable systems on quiet planets on predictable orbits around unchanging stars. And in most cases, it does. But sometimes, under the right conditions, it allows something else to emerge. Something that exists right at the boundary, between expansion and collapse, between cohesion and disintegration, between being and no longer being. HAP-P67b exists at that boundary. For a brief moment in cosmic time, it becomes one of the largest planets we have ever observed. A vast, inflated structure shaped not by excess material, but by extreme conditions, and then it fades. On a timescale shorter than the age of life on Earth, it will be gone. So the largest planet is not the strongest, not the heaviest, not the most dominant. It is one of the most fragile, and that is the unsettling truth at the center of this story. Not that the universe is vast, you already knew that. Not that it is strange, you expected that. But that scale does not guarantee strength. That something can be enormous, and yet barely held together. That the word planet, which we associate with permanent, can also describe something temporary, something fading, something already in the process of disappearing. A cloud of gas, thinner than intuition, allows drifting away in silence around a dying star. More than 1,200 light-years from everything familiar. So the next time you hear about the largest planet in the universe, remember this. It is not a fortress. It is not a giant. It is something far more fragile. A vast, hollow presence, shaped like a world, already slipping away. And the fact that it exists, at all, even briefly, even now, is one of the most extraordinary things the universe has ever done.